variable acceleration with vectors in 2 dimensions. Example 2. So we start off with the velocity vector for a particle. We have to work out its position vector. So starting with velocity, we integrate our vector with respect to time, we get the position vector. Integrating, so we take the I component, integrate the 3t, so we get 3t squared over 2 times I. We do the same with the j component, and the constant of integration will also be a vector. Initially, when t equals 0, we're given the position of the particle, 2i minus 3j. So we substitute in t equals 0 in here, and the position 2i minus 3j goes in here. And these are both 0. So this is our constant of integration in vector form. Now we substitute this back into here, so we have the position vector with the I and j components collected together, and if you want you can put the units in as well. Example 3. We start off with the acceleration vector this time, and we want to work out the position vector. So we start here with the acceleration vector, we integrate once to get the velocity vector, we work out the constant of integration, we integrate again to get the position vector, and we work out the constant of integration again. Integrating the acceleration vector, we get the velocity vector. To work out the constant of integration, we're given that at t equals 3 seconds the particle had a velocity of 6i meters per second, so we put t equals 3 in here, and v equals 6i will go here. We simplify, so our constant of integration in vector form is minus 6i plus 9j. We substitute that back in to our velocity vector, here it is, and then collect the I and j terms together, and this is what we're looking for. Part C, we have to work out the angle that the velocity vector will make with the vector I at the instant when t equals 2. So substituting in t equals 2 into our velocity vector here and here, and simplifying, gives us v equals 2i plus 5j meters per second. So to work out an angle, we need a triangle like so. Here's the velocity vector, here's the vector I, and you can see it's the angle theta that the vector v is making with the positive I vector there. So tan theta is equal to 5 over 2, so tan inverse of 5 over 2 gives us 68.2 degrees. Part D, to work out the position vector, we integrate the velocity vector. So we're going to integrate. That's now done, and I'm using a different letter for our new constant of integration, again in vector form. At t equals 3 seconds, we're given the position vector, so we substitute in t equals 3 into here, and 20i plus 3j is the position vector, that goes here. Then we can work out the value of k. Simplifying, so vector k is equal to 20i minus 15j, and now we should go back to our position vector and replace the k with this vector. Again, it's more useful to have the I and j components grouped together like so. So this is our position vector for any time t. At t equals 0, so the initial position of this particle, so that term is 0, this term is 0, we're left with 20i, 0, 0, we're left with minus 15j. This is the initial position vector of the particle. So using Pythagoras' theorem, we can work out the magnitude of the initial position vector. So we get 25, so the particle was 25 meters from the origin. And just remember that the vector r represents position vector and s represents displacement. And sometimes they are the same. That's if a particle starts from the origin initially, so that's when t equals 0, then they will be the same. And if the particle starts elsewhere, like in this case, then displacement and position vectors are different.